One and all present here. So good afternoon to one and all present here. I would like to thank the organizers and the sponsors to give me this platform to present my work. So I am Vatsala from Delhi Technological University. I am a research scholar at the Department of Applied Physics. So I will be presenting on the interpretable machine learning for feature importance in anomalous Hall effect predictions. Okay, so I will start with the traditional and the machine learning regime, then coming forward to the feature selection and optimizations. So first of all, uh, as in the previous talks, professors has already talked about the anomalous Hall effect. Giving in brief, basically anomalous Hall effect is present in the magnetic materials where magnetic materials where we observe a transverse voltage that is produced perpendicular to the external current and the magnetic field. When there is no external magnetic field is present, it is because of the intrinsic magnetic field that is present. So it governs on the two parameters, that are the Barry curvature and the scattering parameters. So there are two type of scattering parameters that governs the anomalous Hall effect. One is the skew scattering, and another is the sideways side jump scattering. So moving next. So basically, what we do in our traditional phenomena, that we take the materials from the materials project, and then we run the DFT calculations on those materials. Then we can construct the Hamiltonian for them. We do the linearization, and then we perform the conductivity calculations, and then later coming to the AHA analysis. But what we are doing in our machine learning workflow was we took the material we took the database from a literature based paper that was on the high throughput AHE, and in that paper we got 2871 materials that were categorized in the class of AHE positives and the negatives. And another database was the Ricken Trip Magnets database, consisting of 6220 materials. So it is a supplemental, we can say it is a supplemental database that is present in the materials project database. And then we then we applied some filters like the zero band gap and the binary and ternary only materials. And then we fetched the materials from the materials project database, and we made a combined data set of 22,875 materials, out of which we were having some null values. So we cleaned that data set, and later on we came to 22,873 materials. So on that we performed the covalent and polar covalent filtering, and the numerical descriptors were then categorized into some classes. And then we performed the ED analysis and trained the model. Then we performed the class imbalance handling and the hyperparameter search using the 5-fold stratified k-fold modeling. Then later on we performed the decision threshold at a decision threshold of 0.5, and later performed the ablation studies, where we target the study on the target study group study, and feature engineering ablation studies were performed. So this workflow is already discussed by me in the previous slide. Later coming on to the feature selection. So we basically divided the features into seven different classifications. That was in structural and size. Count was 5: symmetry, energetics, magnetism, lattice geometry, electronegativity, bonding, and the derived composites that were designed by us. That was the engineered features. So this is the EDA analysis that was performed. So the first figure that is shown there shows the AHE positives, and the gray part shows that these materials were not present in our database, as mostly of them are the radioactive materials, or the lanthanide or the actinides. So these were not present in our database. And as we can see that the transition matters are showing the more prevalence, more frequency that were appearing in our database. Later, the crystal symmetries, as we can see that the for cubic, the AHE positives are very high, showing that the simpler the crystal symmetry was there, the better the model was performing. And similarly for the ferromagnets, as we know that the AHE are for AHE, the ferromagnets works very well. So that's what is shown. This EDA was performed before the training of our model. These also shows the frequency dispersion. So from the first figure that we saw for the N sites, so we see that the AHE positives are very high at the around the median of 4. So this shows that the number of sites that were emerged were the critical features that we find through our model. So the distribution shows that many of the detected materials with fewer sites are more likely to display AHE, because they were showing because of the crystal symmetries and the factors that were governing. So the Barry curvature for these materials were uh, higher. So the insight, so the feature insight is showing the more prevalence. Similarly, we can see that this total magnetized normalized volume, this was not considered as a better feature, and these frequency distributions were seen for the features. So this is the Pearson correlation matrix where, okay, sir. Okay, in this in this Pearson correlation matrix, we saw that the features that were highly correlated are shown in the red, right? And these were the threshold dependent matrices, that is accuracy, precision, recall, F1, and ROC AUC and PR AUC were the independent matrices. And these were the ROC curves that we get for the feature importance for our model. These were the precision recall curves, and these were the feature importance that we got from the model. That is, for logistic, we got the science standardized coefficients, where we see that the positives are for the higher important features, and the shown in the blue, we can treat them as outliers. Whether the in the XG boost model, the gain was taken for the feature importance. For SVM, it was not done for the feature importance, but on the permutation on validation. And for the random forest, we took impurity as a feature importance, that was the Guinea impurity. And for the cat boost, we saw for the prediction value changes. So from all of these, these are the feature ablation studies that I already talked about, that the target group and the feature engineered studies, that is for all the models that I performed. The ablation studies were only performed on the logistic regression, XG boost, SVM, not on the SVM, random forest, and the cat boost model. So these were the results that I got. And from here, I would like to conclude that the model XG boost and the logistic regression were showing the highest accuracy, and we got multiple features that were important, like the crystal structure, electronic structure, magnetism, bonding, rather than any single descriptors and the insights that we already saw in last slides. So these were the references taken by me, and I would like to acknowledge my supervisor, Dr. Mukhtiar Singh, and the financial support by ANRF and the National Supercomputing Mission, NPSF, CDEC, Param Siddhi AI, and MIT for giving me this opportunity. Thank you. Thank you. A quick question? No. So I think we move to the next one, Omkita Bajumdar, right?
Good afternoon. Good afternoon, everyone. I am Ankita Majumdar from VCC Kolkata, and I'm a third year PhD scholar under Shashi Srivastav. So these are the today's overviews where I am going to talk about I'm first going to introduce the model we have used, then the background studies what are already available in the literature. Then I will show the results and explain all the counterintuitive features through analytics. Then the experimental outlook and conclusion. So the people here will be thinking that what is a quantum battery? So uh, quantum battery is a microscopic energy storage device which utilizes the superposition principle to store energy within it under unitary evolution. And here we are going to use we have modeled our quantum batteries at the kicked rotor, free kicked rotor. So described by the Hamiltonian pi square by 2 mu I. Due to computation limitation, I have only used two kick rotors for now. But okay, so there are two charging protocols available in the literature. One is the charger mediated protocol, and another is the direct charging protocol. For charger mediated protocol, you need a charger where the qubits are connected within it to it, and then some global quench is performed, and then we take partial trace with respect to the charger and expect the battery at some higher excited state. And the other one is the direct charging protocol where we do not need a charger, rather all the batteries are charged through global entangling operations by introducing interaction among themselves. So here we have used the direct charging protocol. The rotors are charged by introducing a interaction in the position space, and ki here is the control parameter from integrability to chaos, and k is the interaction strength between the rotors. So here we have used the initial state as the zero momentum state, and the energy stored within the ith subsystem, such as so we have considered two rotors, and one rotor is partial test with already partial test out, and we are left with another rotor. So the energy stored within that rotor is given by this equation. Is given by this equation. Rho I zero is the ground state of the rotor, and rho it is the time evolved state. Here we have considered delta kick charging protocol. So the unitary takes this kind of expression. Now from this stored energy, how much we can extract is given by the ergotropy. So ergotropy is the maximum amount of work that can be extracted through unitary cyclic evolution from a quantum system. And this is the mathematical framework of performing the ergotropy. So you can see ergotropy is always bounded by a passive state, and passive states are formed by in mathematics it's very easy to form. So the ascending order, so eigenvalues of the row are in ascending orders and goes to the energy eigenvalues eigenstates with descending orders energy. So we can see that only when the system uh, passive state falls with the ground state, then only we can extract all the ergotropy or the stored energy. So efficiency is what? So efficiency is basically the ratio between the ergotropy to the stored energy. So the background is let us now discuss what is the relevance of this work. So it was thoroughly argued that the systems which exhibit unit efficiency must remain in the near integrable or integrable regime, and this is argued in the first PRL paper I have cited. So conversely, quantum chaos always affects negatively to the efficiency of a quantum battery. So we are here we so we want to impose a question that does there exist any genuine quantum mechanical phenomena which can optimize efficiency even when the system's classical phase space is completely chaotic. So this is the result where to compare the results with the off-resonant one, we have considered two sets of parameters where in the off-resonant case, we have considered h bar tau is 1 equals to 1, where tau is the time period between two successive kicks, and h bar tau equals to 4 for resonant case. H bar tau equals to 4 pi L by L prime, where L and L prime are two co-primes, and when they take the value 1, it corresponds to the first order resonance. But it is worth mentioning that all the results shown here are for even for first order resonance, but it is robust for higher order resonance as well. So as I have seen, as I have told that the system which exhibit efficiency 1, unit efficiency, the passive state must fall to the ground state. So here we have verified by two quantities. One is the von Neumann entropy and another is the fidelity. Fidelity we have calculated between the passive state, time evolved passive state, and the ground state. So you can see that the system is completely mixed, and uh, I want to emphasize that the von Neumann entropy shows superlinear growth, initial superlinear growth, then followed by a logarithmic one to saturate the maximum value. And the fidelity is also falling. So the system is not pure, but it is completely mixed. So this seems counterintuitive, but let us focus on to make this intuitive. To make the so this seems counterintuitive, but let us now focus. Explain through analytics to and focus on the passive state energy rather than the passive state itself. So here we have considered analytics where we have performed through the where we have performed the coordinate transformation for k1 and k2 not equals to 0, and we have got the energy expression as given by this, and you can see it depends upon k2 and k as well, where k2 is the kick strength of the rotor, and so to make the system chaotic we have to consider k2 very greater than 1. But conversely, in the passive state energy depends only upon the interaction strength, and when so this is the Schmidt eigenvalues square of the Schmidt eigenvalues for rho when Ki is completely zero. So individual kicking strength is zero. So passive state energy only depends upon the interaction strength. And so in the case for k ki very greater than k, we can have unit efficiency, and this is the expression for the efficiency, and we can see it completely matches with the analytics. So next time experimental outlook. So here we have considered in interacting kick tops where we have also taken the kick tops to the resonance case, and for the initial state we have considered the lowest energy state, that is the ground state, and here also entanglement grows superlinearly with time, but the efficiency we get close to 1. Now, the conclusion, I want to say that resonance can bypass the effect of chaos, and through analytical expressions, we have established this. And next, we have provided some interacting TikTok to show the experimental outlook. Thank you.
Good. We now come to the any question, comment? So we now come to the last. Thank you.
Thank you.
Last presentation by Chetna Sani.
Good afternoon, everyone. I am Chetna Sani, a research scholar of Department of Chemistry. Working under the supervision of Professor Hemsi Kanpar at Indian Institute of Technology, Roorkee. The title of my presentation is Orthorhombic KMGX Semiconductor as Promising Photovoltaic Materials, a first principle analysis. Here is a quick outline of my presentation. I will start with the research motivation followed by the discussion of my result, that the how pressure induce a phase transition, stability of unexplored orthorhombic phase and its photovoltaic potential. Then I will conclude at the end. Let's start with the introduction to KMGX, an emerging multifunctional material which exists in tetragonal phase. This is the ground state phase of the KMGX family, explored for several applications including thermoelectric, topology and photovoltaic. The other predicted phase of the KMGX family is hexagonal, exists in both polar and non-polar structure form, suggesting its potential for the ferroelectric application. After that, the next phase is the cubic phase, which is explored for these two applications, thermoelectric and photovoltaic. And the next phase of the KMGX family is orthorhombic phase, which remains largely unexplored for the KMGX family. Although many ternary compounds exist in this phase, so this motivates us to explore these phases. Since this orthorhombic phase is the translational Gleick subgroup of the experimentally reported tetragonal phase, so it can be assessed through a phase transition. So the main objective of this work is to investigate the possibility of pressure induced phase transition, verification of stability of its orthorhombic phase and exploration of its photovoltaic potential. So for this we used a first principle approach based on density functional theory, which states that energy can be mapped as a functional of electron density. So with the by solving this equation we evaluate the properties of the material. Although the standard DFT give excellent results for the ground state property, but it underestimates the electron hole pair interaction and do not give the correct band structure. Now, to obtain the accurate excited state property, we go beyond DFT. We first incorporate the Z0W0 approximation, which correct the band gap, but it still do not include the excitonic effect. To include the excitonic effect, we solve the Bethe-Slater equation on top of Z0W0 to explicitly include the electron hole pair interaction. Therefore, to evaluate the optical properties of the material, we rely on this Z0W0 with BSc framework. So with this framework, we will discuss the first part of our methodology, that is unlocking the orthorhombic phase via the pressure induced phase transition. For all the structural phases of KMGX, we plot the equation of state curve. Here the blue line represents the tetragonal phase while the green line represents the orthorhombic phase, and this crossing represents the possibility of phase transition from this tetragonal phase to the orthorhombic phase. And at this crossing, we calculate the pressure, phase transition pressure, which is summarized in this table. So this is the condition for getting an orthorhombic phase of the KMGX family. So after assessing the condition of getting the orthorhombic phase, we pass our material through the four pillars of stability check, that is static, thermodynamic, dynamic and the mechanical one. Since the static stability of the compound is already confirmed through the energy versus volume analysis, so we next explore its thermodynamic stability. And it's investigated by calculating their per atomic change in formation enthalpy. And for all the KMGX compound, we calculate its formation enthalpy for all the existing phase and its decomposition structure. And here, this color contouring help us to visualize the location of minima, and we see that for all the KMGX compound, this ortho phase is stable. So we can say that the all KMGX compound are thermodynamically stable above the transition pressure. So after that, we discuss the dynamic stability, which is evaluated through this phonon band structure. And for all the KMGX compound, there is no imaginary frequency mode are observed through the high symmetry path of the billion zone. So I can say that all the KMGX compound are dynamically stable. After that, we discuss the mechanical stability of the KMGX compound. And for the orthorhombic system, we get 9 independent elastic constant, which is summarized in this table, and follow this bond stability condition. Thus, we can say that the all KMGX compound are also mechanical stable. So, after assessing its stability through this mechanical, dynamic, static, and thermodynamic study, we next discuss its property. So this is the electronic band structure for all the KMGX compound, where this first 3 compound shows a direct band gap in the visible range, whereas this KMGBI shows a semi-metallic behavior. Therefore, for further photovoltaic application, we focus these 3 compounds and explore its optical properties. We first calculate the real and imaginary part of dielectric constant, which help us to investigate the absorption coefficient of the material. And for KMGX, it shows absorption peak near the absorption onset in the visible region. So this high value of absorption coefficient suggests that all the KMGX compound are a promising candidate for the photovoltaic application. So we will next discuss how efficiently they absorb the light and convert it into electrical energy. For that, we calculate the efficiency of the material by using the spectroscopic limited maximum efficiency approach. By using this formula, we calculate the SLME values for all the KMGX compound, where the numerator value indicates the total output power density, which is obtained through this current volume analysis, and this denominator part indicate the total incident power density. As shown in this diagram, the SLME value increases and gradually saturate, and the KMGSB and KMGAS show the higher SLME value as compared to KMGP. So these results indicate that these 2 candidates, that is KMGAS and KMGSB, are the promising candidate for the photovoltaic application. So after discussing my result, here I would like to conclude the findings of my work. First, the pressure unlocked the unexplored orthorhombic phase of the KMGX family. Second, the predicted orthorhombic structure satisfy all stability criteria, and these 3 compounds shows a direct band gap in the visible range, and the KMGAS and the KMGSB achieve the high photovoltaic efficiency. So this finding reveals this pressure engineered orthorhombic KMGX as a new class of multifunctional material. So here I would like to acknowledge my Professor Himsi Kanpal and other lab members, the Chemistry Department of Indian Institute of Technology, Roorkee, the Ministry of Education for providing me the financial support, the supercomputing facility of IITR, and the QMAT 2026 for providing me this great opportunity. Thank you.